Bismillahirrahmanirrahim. Today we will cover lecture number 22 of Mechanism Material 2, and it is just about some introduction, definitions, and a little bit derivation for impact loading. So it is very easy lecture, and it is just about some informations and concepts. Creep and fatigue, impact loading, introduction to fracture mechanics. Creep: when a material has to support a load for a very long period of time, it may continue to deform until a sudden fracture occurs or its usefulness is impaired. This time-dependent permanent deformation is known as creep. Normally, creep is considered when metals and ceramics are used for structural members or mechanical parts that are subjected to high temperature. For high temperature, normally for high temperature, but not always. For some materials, however, such as polymers and composite materials, including wood and concrete, temperature is not an important factor, and yet can creep can occur strictly from long-term load application. For these materials, like polymers and composite material, creep is just due to long load application. Long term means more time is involved. As a typical example, consider the fact that a rubber band will not return to its original shape after being released from a stretched position in which it was held for a very long period of time. For practical purposes, when creep becomes important, a member is usually designed to resist a specified creep strain for a given period of time. An important mechanical property that is used in this regard is called the creep strength. So, important property is creep strength. This value, creep strength, represent the highest stress the material can withstand during a specified time without exceeding an allowable creep strain. So, without exceeding the creep strain, for this period, it will withstand. For a specified period, it will withstand the highest stress. This will call as creep strength. The creep strength will vary with temperature, and for design, a temperature, duration of loading, and allowable creep strain must all be specified. For example, a creep strain of 0.1% per year has been suggested for steel and used for bolts and piping. So this is the value for steel using in bolts and piping. Several methods exist for determining the allowable creep strength for a particular material. One of the simplest involves testing several specimens simultaneously at a constant temperature, but with each subjected to a different axial stress. So this is one way. By measuring the length of time needed to produce the allowable creep strain for each specimen, a curve of stress versus time can be established. Normally, these tests are run to maximum of 1000 times. An example of result of stainless steel at a temperature of 1200 Fahrenheit and prescribed creep strain of 1% is shown in this figure. So, sigma T diagram, stress time diagram for stainless steel at 1200 Fahrenheit and creep strain at 1%. As noted, this material has a yield strength of 40 ksi, 275 megapascal at room temperature, 0.2% offset, and the creep strength 1000 hours is found to be approximately SC sigma C is equal to 20 ksi, 138 megapascal. For a longer period of time, extrapolations from the curve must be made. To do this, you will require a certain amount of experience with creep behavior and some supplementary knowledge about the creep properties of the material. Once the material's creep strength has been determined, however, a factor of safety is applied to obtain an appropriate allowable stress for design. So, this discussion has been extrapolation can be made by experts to predict the creep behavior. So this is about creep. Then fatigue. When a material is subjected to a repeated cycle of stress or strain, it causes its internal structure to break down, ultimately leading to fracture. This behavior is called fatigue, and it is usually responsible for a large percentage of failure in connecting rod, crankshafts of engines, gas turbine blades. Correcting connections or support for bridges, railroad wheels and axles and other parts subject to cyclic loading. In all these cases, fracture will occur at a stress that is less than the material's yield stress. The nature of this failure apparently results from the fact that there are microscopic imperfections. So fatigue is due to some microscopic internally crack and microscopic imperfections are there, from where the crack will propagate and will cause the failure. Usually on the surface of the member, where the localized stress becomes much greater than the average stress acting over the cross section. As this higher stress is cycled, it's lead to the formation of minute cracks. Stress is cycled. When it is repeated again and again, minute crack will be developed. Occurrence of these crack causes a further increase of stress at their tips. So at some point, stress concentration will be there, at especially at the tips, which in turn cause a further extension of the crack. So as a result, crack will enhanced into the material as the stress continue to be cycled. Eventually, the cross-section area of the member is reduced to the point where the load can no longer be sustained, and as a result sudden fracture occurs. So if crack is there, remaining area is bearing the stress. So when crack is enhanced, remaining area will be, cross section area will be less. So as a result sudden fracture will be there. The material, even though known to be ductile, behaves as if it were brittle. So material was ductile, but in this in this condition, it behaves like brittle due to crack propagations. In order to specify a safe strength for a metallic material under repeated loading, it is necessary to determine a limit below which no evidence of failure can be detected after applying a load for a specified number of cycles. This limit in stress is called the endurance limit, so or fatigue limit. So number of cycles which can be sustained, which can be without failure material can withstand, that is the endurance limit. Using a testing machine for this purpose, a series of specimens are each subjected to a specified stress and cycled to failure. The results are plotted as a graph representing the stress S or sigma on the vertical axis and the number of cycle to failure n, number of cycle to failure, first cycle, second, third, and the number of cycle and on the horizontal axis. The graph is called SN diagram or stress cycle diagram, and most often the values of n are put on logarithmic scale since they are generally quite large. So what logarithmic scale do? It will shorten the large quantity. So, like here it is in log, so you can show here just from here to here, very small scale, you can show more quantities like 500. It is logarithmic scale. Example of a diagram for two common engineering materials are shown in figure. Two materials, aluminum and steel. This is the behavior of steel, this is the behavior of aluminum. This is 27 for steel and 19 for aluminum, because after that it is in this way, it can 27 stress, 27 is stress for steel and 19 is stress for aluminum. The endurance limit is usually identified as the stress for which the SN, it is stress for which the SN graph becomes horizontal or asymptotic. Asymptotic means straight, so it is horizontal asymptotic. As noted, it has a well-defined value of SSL. Sorry, it is EL. It should be EL of steel is equal to 27. First, when it is 6 megapascal for steel. For aluminum, however, the endurance limit is not well defined, and so here it may be specified as the stress having a limit of say 500 million cycle. It is EL. Elastic EL. As EL of aluminum is equal to 131 megapascal. Once a particular value is obtained, it is often assumed that for any stress below this value, the fatigue life will be infinite. So below this, the fatigue life is infinite, and therefore the number of cycle to failure is no longer given consideration. So if you design below this stress, so material will not fail. Its life will be infinite. Now, very small, easy topic, impact loading as name. So it is for very short period of time and it is dynamic, not static. Some loadings are dynamic, such as when one object strikes another, producing large forces between them during a very short period of time. If we assume that during the collision no energy is lost due to heat, so we assume there is no loss due to heat while cooling occurs, sound or localized plastic deformation. So there is no loss. Then we can study the mechanics of this impact using the conservation of energy. So law of conservation of energy will be used when there is no loss. So first example, falling block. There is diagram is shown. This is block fall on spring. This is like H, and after this maximum deflection of the spring. Consider the simple block and spring system shown in figure. When the block is released from rest, it falls a distance H, striking the spring and compressing it a distance delta max before momentarily coming to rest. If we neglect the mass of the spring and assume that it responds elastically, then the conservation of energy requires that work done by the block weight falling H plus delta max be equal to the work needed to displace the end of the spring and amount delta max. Since the force in a spring is related to delta max by F is equal to K into delta max, where K is this spring stiffness, then UE will be W into, that is 8 into H plus delta max, total displacement, is equal to 1 over 2 K delta max into delta max. Actually we are replacing this force, and half is due to gradual, so it will become 1 over K delta max square. And I think you have done in this in some school or college physics. So from here, after you will have this relation. Solving this quadratic equation, when you solve quadratic equation, maximum root is delta max is equal to W over K plus square root of W over K square plus 2 into W over K into H. If the weight W is supported statically, now we are supposing if it is statically, actually this is done dynamically, but if we suppose it is statically by the spring, then the displacement of the block is sigma stationary is equal to W over K. Using this simplification, the above equation becomes delta max is equal to delta st plus square root of delta st plus 2 delta st into H. Delta max is equal to delta S. Taking common, this will be the equation. Once delta max is calculated, the maximum force applied to the spring can be determined from the F max is equal to K into delta max. So it can be determined. For another example, sliding block, using a similar analysis, it is also possible to determine the maximum displacement of the end of the spring if the block is sliding on a smooth horizontal surface with a known velocity v just before it collides with the spring. Here the kinetic energy will be transformed into stored energy in the spring. Hence, this is the block. So when it strikes same delta max, this is the spring constant plus stiffness K. U is again conservation of energy, 1 over 2 into W energy into V square is equal to 1 over 2 K delta max square. So from here delta max will be W is equal to K. Since the static displacement of block resting in the spring is again W spring, W will be K ST. So when you put here, this will be the result. So from this loading we can find maximum deflection associated force, and it is for a very short period of time. Then last but not least, about introduction to fracture mechanics. Actually this is a subject taught in but here we are must just have this slide to just have the idea about fracture mechanics. As name indicates, fracture means where the material rupture last point on the stress strain diagram. So what will happen? Obviously there will be some cracks and propagation of crack and all these type of study will be done in this fracture mechanics. So according to this Wikipedia content, fracture mechanics is the field of mechanics concerned with the study of the propagation of cracks in materials. Propagation of crack, as I said, it uses method of analytical solid mechanics to calculate the driving force on a crack and those of experimental solid mechanics to characterize the material's resistance to fracture. There are three ways of applying force to enable a crack to propagate. Mode 1, opening mode. A tensile stress normal to the plane of the crack will open the mode 1. Mode 2, sliding mode. Shear stress acting parallel to the plane of the crack and perpendicular to the crack front. And third mode is steering mode. Shear stress acting parallel to the plane of the crack and parallel to the crack front. Sliding parallel to the plane but perpendicular to crack front. If you both are parallel, mode 3. And there are many other mode of failure, but what happened in fracture nowadays, this is very important and hot topic for research. That is about fracture mechanics. Thank you.